everybody. Welcome. And this is Open Research Institute's Projects Meetup. It's the 10th of March, 2026. And what we do here is we talk about what we've done over the past week or so and what we have planned over the next week or so. And if we have any roadblocks, anything getting in our way, preventing us from doing what we want to do. And if we need anything, if we need any resources, at least that ORI can help provide or that we can line up for you or put in a good word. And we have plenty to report. Aaron from OpenCPI, he's got a pretty good report here. He'll be probably going to be late. So what I'm going to do is I'm going to read in what he has summarized for us. And he has cleaned his desk. And I would like to acknowledge this as a huge step forward because all of us are in awe of this. When you actually can hit either floor or desktop, that is a good thing. So he's cleaned his desk right on. He has completed a DVB S2 transmission on a ZC706. Big deal. So DVB, or Digital Video Broadcasting for Satellite version 2, is the open standard that we use for our downlink in our satellite projects at Open Research Institute. And what he's doing is leveraging our VHDL encoder written by Swato and other folks. And he has taken this into OpenCPI and made it work. And he's made it work on a very capable set of hardware. This is the ZC706, and this is a dev board from Xilinx that has a very powerful zinc chip on it. So the transmit now working. We've seen this over the past, I would say, 3 weeks. We've started to see it come alive in his reports, and the completion of transmit, good solid transmit, is a big milestone. But it doesn't end there. He has created a continuous integration, or CI, pipeline. And this term of art means that what you do is you set up a testing scenario where you're constantly testing the integration. So he's created a CI pipeline to generate OpenCPI project documents, and you can view them at the website. It's https ocpidocs.oliveras.info. I went there, looks pretty amazing. So he's generated a way to continuously update the documentation automatically. And he's worked on a continuous integration pipeline to generate the SD card artifacts for LibreSDR, ZCU102, and the ZC706. These are all of the dev boards and prototyping SDRs that we use. So this is a continuous integration pipeline where he makes a change, he makes something work, and it automatically generates the SD card artifacts. And what we do in remote labs is generally manually generate the SD card artifacts. What I do when I take a VHDL design for, say, Opulent Voice, and I generate it for LibreSDR, I say make, and then I say pay. I want you to make for the platform LibreSDR. And it does it. And then I say, oh, hey, by the way, make SD image. And it does. And so what Aaron's done is to automate this process. So anytime that there's an update, you have the SD card artifacts there. And SD card is the memory card that goes into a lot of these devices. A lot of times as a developer, you have to manually copy over the files to the SD card, take it over to your device, put it in there, reboot, blah, blah, blah. Might ever so often it doesn't work. Sometimes, most of the time it does. Okay, so what he's done is automate that process. And so for the future, what does he plan to work on? To complete the artifact generation continuous integration pipeline. So to go ahead and complete this, he's worked on it, sort of working, going to complete it. He wants to write a detailed instruction on how to replicate this demo. This is gold. So being able to duplicate the work is what we're after. And he started working on incorporating the receive side, that's big. We put out the word that, hey, we got this encoder. We've had it for a number of years. This is our downlink. We also want a receiver. So he started working on incorporating a receiver and to send the Spectrum viewer through the downlink via UDP to display it at the receive end. Very cool. Okay. If a picture is worth 1,000 words, then a video is worth 1,000 pictures. So you can see that there's a lot of gain there. And it has a screenshot that I'm going to stitch it in to the video, but it shows a clean desk and and his setup and a lovely signal. So I'm really looking forward to being able to share that. Okay, so that's the OpenCPI update from Aaron, and this is focused on our satellite side. So when we're talking about Hyperia, we're talking about the satellite side or the ground sat, what we call a ground sat sides. This would be like a central node, terrestrial node, or a satellite node. So that's what we're talking about. So downlink work. This is after you collect all of these wonderful Opulent Voice or whatever else signals that we can rake in and deal with and organize. And then we load them up into DVB S2 frames. And then we send them on the downlink. And then at the receiving station on the, your ground station, you're able to see anything you like. You're able to search through and pick through and decide what you want to talk to, who you want to talk to, what you want to see, everything, a focus list, whatever. Okay, and all right. So, any questions? Does anybody have any questions for Aaron? We'll go ahead and you can ask them, and then we'll just record them here. It's all really good work. Okay, all right. Nothing heard. All right, so I have an update on AMSAT UK support for the mode dynamic transponder. This is a successive interference cancellation or signals intelligence type of design for the FunCube Plus. And it also has relevance to Hyperia because what we're doing is developing a design that can be configured for either scanning, like a signals analysis or signal analyzer, or a communications channel. And the difference there is whether or not your different channels overlap and provide a smooth response over the entire bandwidth, or you channelize and you have gaps in between or guard bands. Our design handles both of those cases. But I'll go ahead and delay that because I'm hoping that David will be able to join us today. And just in case that he's able to join us a little bit late, then I'd like to skip ahead to the Opulent Voice updates. So we did solve a bug in HCL with the preamble accidentally stomping things, and we have confirmed that has been fixed. There's been a couple of other updates to the software modem, so I'd like to go ahead and maybe turn it over to Paul and Matthew to talk about that.
Okay, I will pitch in a little bit on that. I did spend some time earlier this week since the last meeting doing testing of that. Or testing so far is maybe a bit of an overstatement. Demoing. I've been running the basic test cases, and holy smoke, they work. We've reached a point where you can send a message either direction with both modems. They hear each other. They do the right thing. They don't generate a lot of garbage. Okay, so that's really nice. It's nice to see. And this inspires me to do more testing because it needs more testing. Um, and I haven't actually done many more testing this week, but I've thought about it and made some planning. And there are a couple of different axes that I want to improve the testing in. One is simply repetition. I need to test over and over and over again to make sure that things are consistent and always work the way they worked in my short little one-off demo earlier this week. And I'm thinking about creating a little software component that I'm toying with calling the chat-o-matic. And this will be a thing that sort of uh, plugs into the block diagram in the place where interlocutor plugs in, which generates and receives encapsulated frames and then pushes and pulls those from Dialogus running in the embedded ARM in the Libre SDR. And something's corresponding to that for the software modem. Maybe two separate developments for that, or maybe the same. Haven't decided yet. And what it does is generate lots and lots of short messages, chat messages. Uh, there'll be different lengths, there'll be different spacings, they'll have different contents, and it should be able to just generate them and generate them and generate them while something else is going on in my head. So it can do a self-sustaining test for possibly long periods of time. And we should easily test thousands, tens of thousands, lots and lots of short messages. And then it'll also be hooked up to another Libre SDR, which can receive them and then check the results. Make sure that they all got through. They didn't get mangled. We didn't have too high a loss rate, and uh, that will be a test. That'll be something real that we can point at and say, look, this works reliably. And if it doesn't, then it'll be stuff we can fix, which is even more important, possibly. Uh, Another dimension I want to test in is over signal strength. I'd really like to see how it behaves when the signal strength gets too small, ragged, sort of to get raggedy on the threshold. I mean, any digital system that's been debugged and basically working will sound great and work great when the signals are strong. But signals aren't always strong in the real world. And it's nice to find out what happens when signals get weak or start to vary. Some of the existing digital voice modems that we're trying to be better than um, fall apart and start to sound like R2D2 when the signal strength is bad. We want to make sure that doesn't happen with Opulent Voice, or happens as little as we can make it happen. So what I think I need for that is a controllable attenuator. Right now, I have a bunch of little attenuators I can plug in together with SMA connectors, and I've got a couple of, thanks to Michelle, a couple of attenuators that have a knob you can turn in 10 dB steps, which is really too coarse for this work. I need something that can go in single dB steps or maybe even half or quarter dB steps under computer control. And it turns out there's an incredibly large price range for these devices. I found one on AliExpress that looks on the surface, if you believe its specs, to be adequate for this work for $3.43 or something like that, plus an exorbitant shipping price of $6. So under $10 for a little board this big with SMA connectors that can do from 0 to 30 dB in 1 dB steps, which would be perfectly fine. We don't need a large range of attenuations because we're only interested in that band between doesn't work and does work. Above that, we just assume it's going to work. Although the real RF designers for a real radio will have to test up here and make sure it works correctly. But we're interested in what's going on in the modem part mostly at the moment
Yeah, we're
and
interested
at
in
the
where it
threshold.
like fails, where the forward error correction starts to, lose it, where the grip of the other control loops lose. And that is actually a pretty steep wall when you back out and look at the whole range. So
Yeah.
it's a narrow band.
This is a characteristic of all well-designed digital systems. If they're optimized for performance, what happens is they work great until they don't. As analog systems just sort of fade off into the noise, and how much horrible noise you're willing to tolerate is where your threshold is. And usually you end up with arbitrary thresholds like 12 dB quieting for FM. Um, but with that brick wall, you just want to investigate in the vicinity of that brick wall. And so I'm looking at, oh, I didn't get to the other end of the price range. You can also easily spend thousands of dollars on these things. Um, and you'll start to get, a brand name on the front, or, it's a little box usually, maybe a slightly bigger box. Uh, you'll get probably more plausible claims on the specifications. Uh, you can get more channels if you need them. I'm not sure that we do. Um, and some other features, but it's basically the same thing as that $10 thing for $3,000. So we don't need to spend the $3,000, but we might be in the $200 sweet spot, maybe for a little test equipment that's not ridiculously uh, fancier than we need and does this, you know, without breaking the bank. And I might need a couple of them to do a bigger system, but I'll start with one. And then some code to make it work. So these are future plans. I wrote some text on the Slack about what I thought about step attenuators and asked for people to help me think about this. Matthew provided some very helpful thoughts. If there's anybody else out there in video land who has thoughts about picking a step attenuator, please speak up because I'm going to order one pretty soon. And if I order the $10 one and that's a mistake, that's not a big mistake. If
Yeah.
if I need to order a $3,000 one and I don't know why, then tell me now.
And we can
Um,
also ask tomorrow night at the DEF CON meetup. Oh, hey, Valerie.
Hang on. Yeah, that's a good idea. DEF CON meetup might contain some people that have thoughts on that.
Or have surplus gear.
Yes, possibly. We might want to. But for $200, it's probably rather have a new one. But if it's a $3,000 thing, I'll scrounge for local people who might have such a
Yeah.
thing in stock.
Or be able to borrow it.
The
So
local microwave guys might have
yeah.
some stuff.
Yeah,
Okay.
and just to be really clear, we can't cobble this together from our existing attenuators because we have 10 dB steps when we look at our local collection because we have quite a few attenuators, but they're all the smallest we have is like 10 dB, right?
The step attenuators we have, I think they're all 10 dB steps, which is too big a step, and they're also controlled with a knob, and I want to automate it. I
Okay,
want the test to be able to run up and down as other things vary, um, because an automated test is a test you're more likely to run than one that takes time,
gotcha.
or takes human involvement.
Okay.
I think that's where I am this week on Opulent Voice. I'll pass it over to Matthew and see if he has more to add. I'm sure he does.
Hello. Well, I don't have much to add on the attenuator, but I mean, I think that the approach is sound. I was happy to provide some of that information. Um, but I think that'll be really useful, being able to automate tests over, it's a good way to collect a lot of data that we need to collect that can be very tedious otherwise. But as far as opulent or other opulent voice updates, I think that we had the one bug, and it was a bug uh, in that when the TX sync capability is enabled, anytime the PTT was asserted, it would send the configured number of sync bits. And when I first implemented it, I was mainly doing the PRBS, so it didn't really matter that I was stepping on PRBS or not. So it just got implemented incorrectly. So now that we saw I was stepping on the real frames, it was very simple fix to um, have the TX request signal held low while the TX sync bits are being transmitted. So we don't pull any data out of the FIFO and not send it. It's just not pulled out of the FIFO until we're actually ready to send it. So it was a minor fix, but annoying that we had to impact the project. But it's there'll be a lot of this kind of stuff as we go along. And then the other update I have is I've implemented the mean variance lock detector approach. I had been thinking to implement it against the PI controller output, but I initially have implemented it now against the Q arm of the Costas loop. So the idea is we take the mean of the we accumulate the Costas arm, the Q arm accumulator, and we accumulate that over our lock interval and take the mean of that and then take the variance of that and subtract the mean from the variance, and the leftover value is how much the signal is moving around during that period of time. And it seems to work really well. And the thing that's kind of nice with the Q arm is the mean should be 0 once the loop is locked. And we can pretty much see that. In fact, maybe I can share a little bit what this looks like. There's the share button. There it is. Here we go. All right, so this is the simulation waveforms from the simulation. This lower group of signals here is the Q-arm mean variance metric. And so what we're doing is we're taking these are not mean and variance per se. They're just they are metrics that are related to mean and variance. So, I could in a document, I'll provide more details on the equations, but the idea here is for this accumulator Q squared, what we're doing is we're taking the squared value, or we're taking the square of that Q arm accumulator, and then we're accumulating that square over the lock interval. And so we can see that we're accumulating up and in this first interval, and then we reset to 0 and we accumulate up again, and then we reset, and then you can see it gets pretty flat. And then the next thing we're doing is we're accumulating the non-squared value over the lock interval, and then we actually square that, and then we get these metrics here. So this upper value is in effect the variance, and the lower value is in effect the mean. And then we can see over time the variance gets smaller and smaller, and the mean approaches 0. And that's what we want. So we can see here, after we're well into lock, the variance is around 550. And then the mean is 0 and 12 and 0 and 1. So it's staying near 0, which is what we would expect. And so then we just kind of picked a lock value here that's kind of empirically derived. I'm trying to figure a way if we can say what this should be more analytically. But so we could see as soon as this variance value goes below 30,000, which we do here, we get a lock. And so it seems to work pretty well. I might want to implement this again on the PI controller output just to see if there's, how that might look. But we're getting pretty similar performance. We might lock one later if we wanted to use, under, value, say like 10,000 or something. We get a lock later. I just picked the number that gave us the lock about the same time as the previous design. So it's implemented and working. I'm just needing to update the RDL and do some bit width optimizations. And once that's done, I can check it in and we can test it. I did make another update to the Costas IQ metric. So this is the energy metric where we look at the energy in the Q arm, which when we're locked should be close to 0, and the energy in the I arm when we're locked should be much larger. So we looked at the delta between those two, and then once we exceed a certain delta, then we can declare lock. Now in this design originally, it was just we take again, the I values coming in and we square them and accumulate them, and then the same with the Q. And then we were just taking the delta at the end of each lock interval, and then we would compare that to the threshold. And if that delta exceeded the threshold, we declare lock. The problem with this approach is that, again, we're taking the accumulator I coming in and the Q coming in, as the signal level decreases, say if we had a fade or signal level was lower for some reason, then this accumulated value would get lower. And so if we are just comparing this accumulated value to the threshold and the accumulated value becomes lower because the signal becomes lower, we could go below the threshold, and even though we're still locked, we would declare an unlock. If that makes sense. So what I've done here to correct that is effectively, again, I didn't want to do division, so there's a cross multiply. So we end up actually multiplying the threshold by a value, and well, not the threshold, but rather we multiply the well, anyway, we basically normalize these input powers, the accumulator I squared and Q squared. We take the delta, but then the other thing we do is we take the sum. And normally you would normalize this by dividing the delta by the sum, but we don't want to do the division. So instead, I take the sum and multiply it by the threshold, and then do the greater than less than comparison. And so now the threshold is, it's, even though it shows here, it's really a fixed fit number, where if the MSB is 1, it's 1/2. And if the MSB or if the two MSBs are 1, then it's 0.75. And so what we're doing is we're multiplying, basically taking a fraction of the sum, right? And so and then we're getting this energy metric. So, and then we compare this energy metric to the delta, and that's where once the delta exceeds the energy metric, then we declare lock. So we can see this here where the delta is small, the IQ sum is high, and then our energy metric is about 0.875 of the sum. And so
yeah, no, that makes sense because you're trying to prevent it from faking us out.
right. And so then on the next one, we're 520, 5.2 million. But you can see the IQ sum value is nearly the same. And so the energy metric's about the same. And then finally here we switch, we get a IQ delta 6.2 million. Whoop, didn't mean to do that.
No,
And again, the sum is about the same, but it's our energy metric is less, and so we declare the lock. So I mean, this we're getting the same lock delay or time that we had previously, but so I haven't really tested this yet, but I should be able to run some simulations where as if we decrease the amplitude into the design and the delta gets smaller, what we're going to see is the sum gets smaller as well, and then we're taking that fractional amount of the sum as our threshold.
yeah, okay.
So this would be an improvement, and so we shouldn't see any false unlocks
Right.
with this mechanism. So these are the two things that I worked on this week, and like I said, I just have some bit optimizations to finish and RDL updates to make, and then it should be available for testing.
So the question,
Yeah.
how do I test it?
It'll be pretty much, similar to what we've done. What I'm doing is, so there'll still be a single bit in the LSB of the status register that's like everything ANDed. So once everything's locked, that bit will be high. But I'm going to have two lock bits for the F1 for the IQ metric and the mean variance metric, and I'll have two unlock bits. So I'm just adding, everything's the same. I'm just adding an extra bit for everything. And then the default values for the thresholds I've set, so you shouldn't have to make any adjustments to the threshold values. I mean, you can, but I mean, they should work out of the box, as it were. So really the testing would be the same testing you've done already. You'll just have different, like you'll have an additional bit for the mean variance, and you'll have an additional lock delay count time for the mean variance.
Okay, so all I can really do, or all I've done so far anyway, is a pretty coarse measurement of how long it takes from the signal appearing to lock.
Right.
And if I expect not to not change very much with this detector, then okay, that's what I can do. It'd be nice to, I don't know if I can somehow get my hands on more detail about how it's working, or um, some success criteria that I can measure or something like that.
Yeah, I mean, I'm open, like I I think like right now you're getting the two metrics you're getting is the lock value, and you'll have the lock bits will be broken out for the IQ metric versus the mean variance. But yeah, you won't know. I mean, they'll be declared at the same time. Well, they might be slightly different, right? In the simulation, it's 607 to 607, but in the lab, we might see that we're off. It might take maybe one or the other ends up locking an integration period later. So they may not necessarily be the same, but you'd be able to see just by reading the registers whether they were the lock time count. If they're the same, then they declared lock at the end of the same interval. or if they weren't the same, then we know that they didn't declare lock at the same interval. So I mean, it's a bit coarse in that we're looking at the lock time interval. Now, by default, the lock time interval is 128. In the simulation, I've set it to 100. So it's basically the simulation is integrating over 100 bits. I think I'll have to double check mine did in the RDL if I change it to 100. So anyways, we're integrating over 100 bits. We could integrate maybe over 50 bits or 250 bits. We could play with the integration period to see how that affects. I would say that if the integration period's too low, could be pretty noisy, and you might get false unlocks or false locks. But if the integration is very long, then we're not able to see that we've locked. We may be locked well before the integration period's over. So I know it's finding that right balance between too long and too short, so that this is a useful metric to us. And I guess that's just kind of, we'll have to maybe think about the best way to test it and arrive at a useful integration period. But what else do you think could be useful that I could expose for testing?
I have a question. I think that it might address your question. So you're asking like what good tests? If there is there something in here that would indicate to you a quick failure, like if this didn't work at all? Is there a situation that we would be able to identify very quickly where things were going really badly, where it wasn't working as intended? What would we look for?
I think we'd look for instability in the lock detection. And so I've tried to do that in that.
Rapidly, it can't quite figure it out. It's giving us a variety.
Yeah.
Okay.
So
look
like
for that.
we have this unlock signal. And the idea here is that if we're locked and then we come back sometime later and we read it and we're locked again,
Yeah.
we don't know that we could have unlocked briefly between the two reads.
Yeah.
So that's the idea of this bit here, is if you read back and this unlock bit is high, but the lock bit is also high, it means that we've had some unlock event since the last time we read.
Okay.
So that tells us something happened. We don't know how often, because I'm not counting how many unlock events that there were. We could add something like that. But at least we know that there was unlock. So if we're reading the register a lot, and we might see the lock bit going up and down, or we see the unlock bit being active sometimes, then that's going to tell us there's some instability in the locks that we need to understand better. Now we might see if we're doing like threshold testing, right? If we're bringing the input signal down close to threshold, we would expect that to happen.
Yes.
Right. And that's okay. In fact, that's a good test because we should see that happening at some point. And so that would be something we'd want to look at as part of threshold testing, is how stable the lock circuit is when we're getting close to threshold.
Gotcha. Because like the ideal is to pass through the zone of instability fairly quickly. You don't want to have it to be very broad in the horizontal. You want that to be a fairly narrowly defined zone, and that as you traverse up and down through your signal strength, that you are either, so a sigmoid basically function, to separate, to get you away from the middle. You want to get away from the middle as quickly as possible and not oscillate too much. Like that instability area we need to kind of like constrain. And if we look for that kind of first, I think that might rule in or out to keep looking. And if we see decent behavior, then we can go ahead and do some more lab work and to quantify behavior. So it looks like that's the first thing, like establish the stability of this and to see the behavior, and then kind of zero in.
Now there is another diagnostic thing that could be useful, and we could do it with an ILA, or I could put in a buffer. But so right now we have this value, the delta and the sum, but all we're getting is this crude metric, right? If we're locked or unlocked, and maybe we hadn't unlocked since the last read.
Right.
If we did capture these these two values over some period of time, that would be really useful to look at those and say, are we getting, are we, maybe we're locked the whole time, but are these shifting around, or are we getting close to the threshold that we might declare an unlock, or so it could be interesting to actually capture a lot of this data,
Yeah.
and so then we'd have a much more clear picture of how the system's behaving, right? So again, we just have this coarse thing of lock unlock, but we could add this, we could either capture it in a buffer, or we could put an ILA in and capture it. And then
Yeah,
the same thing
absolutely.
with the mean variance. So that would be useful to help, say how stable these are and if they're operating as we would expect over time. That
Right.
that, that would be good.
Yeah, we can totally do that. I think we'll learn a lot over the next week then. This is exciting. And this is for, just so you know, like for people listening, the what we're talking about is the symbol level lock, whether or not we actually are receiving the individual symbols with confidence. Like, because we get all of this energy, coming in at us through our antennas. And then we try to figure out, do we have trash or treasure, and or in between. And we don't really want that in between to be very large. We want to be able to discriminate very quickly whether or not we have a signal or it's trash. And so that's what we're talking about here. And then once we're able to get like a symbol lock, then all of the other stuff that we um, can do further down the pipeline then is done with much more confidence and quality, like the frame lock, for instance. And um, yeah, getting this right is important, and the metrics that we have that you've introduced today that you've added are a huge step forward. I think we can get some really, if we have to, that we can get some really good statistics from the um, from these terms, because what you have is not just the values themselves, but you also have the velocity, essentially, when you're, some of the stuff that you're talking about is it gives us the velocity of the signal, and that's actually really important.
Yeah. Well, another thing, with this is, again, still trying to figure out, go back to our loop gains and get
Yeah,
those, matching in an analytical approach versus our empirical approach. But, even with the empirical approach, this data is useful to see how much the loops are wandering around, right? So,
yeah,
I mean, if we actually had these, lock period values, they would be indicative, their stability, if you will, or their consistency or lack of it, is indicative of how stable the loop is. Um,
absolutely.
yeah. So that could be useful in information in tuning the the loop gains so that we or help optimize them, and
Right.
even if we had it analytical, there may still be some optimization that could be done from the analytical as a starting point. And again, this kind of data, not, you could use threshold, you could use acquisition time. Those are two good metrics, but then even these metrics could also be really useful to, again, evaluate the loop gains.
That's absolutely correct. That's been one of our enduring mysteries. So every week we get a little closer to having it well in hand. Awesome. All right. Any questions for Matthew? Matthew, have it, anything else you want to talk about?
Um, Wait, not that I can think of. That was
That's a lot. No, this is it's deep stuff. So if you're if you're looking at this and you're going, wow, it looks like a lot of control theory, you're right. It is. This gets right at the heart of the matter for control loops and gains and all of that sort of stuff. And we'll just keep plugging away and do our best. And yeah, like what you see in the center of the screen here, it goes from not locked to locked. We want that transition to be as quick and as confident as possible. And that's what all this work is about.
Yeah, and I wasn't showing it. So this is where the lock point is, but we can see, these three curves. This is the PI accumulator, the top one, and the proportional value is the middle one, and then the adjustment value out to the NCO, which is the combination of these two, is the bottom one. So we could see, we're declaring lock here, and the adjustment value, is pretty stable long before, but we could see the accumulator value is just kind of coming down and getting close to being at stable value, and the P is coming up. So this is kind of it seems to me a reasonable point to declare lock. Everything's going to the right direction. And then again, this adjustment value is stable long before. But I mean, so just visually looking at, where the lock is occurring, and we could see, this is these two at the beginning and these two here before they all flatten out, they kind of feels like a good lock point, just looking at it visually.
No, totally. It looks like all your friends show up for the shift at the restaurant and then things settle down. And right about when things settle down is when lock is declared. So looks good to me. It does. It makes an intuitive sort of sense when you back off and look at the big picture. So I like that. That gives us some confidence that we're on the right track.
Yep, very good.
Are there scenarios that we can identify up front that would stress this kind of indicator? Like if I oscillated the signal strength at a certain rate, would that be a useful measurement to make right away, or do we just wait until some problems show up and then try to?
No, I think that would be useful to make right away. I mean, again, if I hadn't had the normalization in, we would expect, if you were modulating the amplitude, that we would expect false unlocks, right? But now if you modulate the amplitude, we shouldn't see any unlocks, and if we do, then that's worth investigating further, or we wouldn't expect to see unlocks. So modulating amplitude, frequency variances, even if we could simulate a Doppler shift, even with some modulating the frequencies of oscillators, that would be useful too.
Yeah, unfortunately, that everybody tells me that I can't use external clocks on these Libre SDRs, which would make it easy to use test equipment to vary the frequency error.
Well, one way we could do it is just, software, could write adjust the NCOs of the transmitter or receiver, like little by little by little, to create frequency outputs.
But as a result, I'm going to get jumps every time I adjust it. I don't know whether that'd be smooth jumps or whether that'd be wildly oscillating jumps. And I might.
Well, I mean, if you're say, I mean, that's a good question. I mean, if we're adjusting it like a fairly crude value, I mean, fairly small value, right? So if we're updating the LSBs, you probably wouldn't notice the jump. If you're pushing, changes much higher it's a 32-bit wide accumulator for the NCOs. So I think the frequency resolution in the LSBs is really low, or really high. So you wouldn't be if you're only twiddling the LSBs, I don't think you'd really notice it. If you're twiddling the MSBs, you would. That would be an issue. So I mean, there's probably some relatively small value that if you updated it enough, you could meaningfully change the frequency, but not have big jumps.
We can always create an input file like from GNU Radio that would give you any scenario you like, including some jammers or, very exotic interference, like a threat model that we probably are not going to face on the amateur bands, but we should go ahead and test. So, I mean, just from electronic warfare, we could probably come up with, files to test where we could run it through its paces. So I'm not worried about finding challenges. We don't have to create it from manipulating the clock. So I think we're in good shape for that whenever we're ready.
Yeah. As far as doing it from another one of our modems, then I don't know what specs Analog Devices has for stuff like that. I know they are aimed at higher data rate and higher uh, more rapidly evolving waveform parameters, for lack of any better term. So chances are anything we want to do will be well within this capability. But I don't know if they actually have specs on how fast you can change the frequency by writing to the accumulator or stuff like that.
Well, let's find
Um, I wouldn't be completely surprised to find out that they zero out the accumulator when you change the step size. And that would be a big jump in phase anyway, and probably throw the lock indicator off somehow, or at least have a possibility to do that. So
Well, what is interesting is this Hutchcart-Schoon's loops, our architecture is supposed to be very resistant to phase jumps, if I remember the paper correctly. So that would actually be an interesting test, just to have a large phase offset come in and see how it handles it.
Yeah, I I'll put it on the list. I think that'd be fun to find out.
yeah, I actually wrote down a couple of other things I wanted to test it over, including, and just happened to have covered them in the last conversation, the other kinds of signal impairments and frequency error.
Excellent.
Um, those would be parameters that the parameter space explodes pretty fast. You can't test them all at once and have good coverage.
Right.
But
It's
at
like
least we can try
Pokemon.
to touch on some of the more interesting ones and try not to get caught with our pants down on some particular uh,
Right.
kind of variance that actually happens in the real world.
Well, we're really close to being able to dive right in, so I'm thrilled. And yeah, I think we can march through a really good test regime and uh, figure out a lot of neat things.
All right.
Awesome.
I think that's all I had for this week.
Well, that's plenty. Thank you so much, Matthew. We couldn't do it without you. This is just wonderful. So very very appreciated. All right. All right. Any questions? And welcome, Valerie. Hi. Anything you wanted to know about, or any particular questions you had,
No,
Valerie?
I'm just being a nosy neighbor. I think you guys are talking way over my head, but in the meantime, thank God for the internet and I can look things up and try to just appreciate you guys. So thank you for letting me just be a nosy neighbor. Thank
Oh,
you.
sure. No, you're always welcome. And for those that don't know Valerie, she's the local chair of the Women in Engineering Affinity Group for San Diego IEEE, and does a lot of other stuff too, tons, and is very invested in artificial intelligence, machine learning, and education. So her specialty is figuring out how to teach engineering and how to teach in general and how to do it better. And that is a big deal and lots of work there. So thank you, Valerie.
Oh, you're so sweet. Thank you. You're the best. You guys, and just listening to you guys, this made like just in a short amount of time, I could look up things and kind of start to figure out what you're talking about. So, I mean, not that I could engage in the conversation, but I feel like a newbie to a new language, and it was really interesting. So, thank you for letting me participate on the sidelines.
Yeah, sure thing. No, in anything you want to know more about, let us know. Just kind of jumping in the midstream is hard, but what we really try to do is explain it in a way that makes it accessible. So yeah, if you want to follow up with me later, anytime. Okay, so the last item that I have before office hours is about the AMSAT UK work. So AMSAT, Amateur Satellite UK, United Kingdom, and this is the big amateur satellite group in the United Kingdom, and they have a satellite coming up called the FunCube Plus, which is a follow-on to the FunCube, which made the FunCube dongle, which a lot of you know about and have. Um, and this particular part of this 2U satellite for educational and amateur non-commercial purposes is called the MDT, or Mode Dynamic Transponder. And how did we get involved? Well, because this is a pretty obvious match for what we do, because it's a digital open source open source digital radio thing. And the purpose of the mode dynamic transponder is has changed a little bit. So originally from the AMSAT UK folks, it was a way to take advantage of sort of a fast uplink and a slow downlink, which is sort of the case when you have a LEO. And the person that became the lead of the MDT kind of envisioned this more as a signals intelligence or a listening station in space for amateur signals on the 70 centimeter or 430 megahertz band. And so we kind of dug into that part of it to try to make that happen. And this week, as of this week, the polyphase channelizer, polyphase or meaning multi-rate handling of digital signals, and this allows you to deal with a large bandwidth in a very organized, methodical way. And our polyphase channelizer for 30 kilohertz of the 70 centimeter band, so this is the satellite in LEO looking down at the Earth and listening to the 70 centimeter band. That polyphase channelizer in VHDL is working. All 7 of 7 test benches are passing. Okay, so you heard about that a week or so ago. We passed the test benches. That's great. So what since then? Well, since this is targeting the ICE 40, this is a fairly small FPGA from Lattice Semiconductor. And the draw to that is the low power consumption. So when we work with Zincs, which all the work that you've heard so far today is about zinc, is on zinc or targeted Xilinx zinc chips. And the power consumption is kind of high, multiple watts at the least. So 2 watts and up. The ICE 40 from Lattice draws less than or at or less than half a watt. And that's the budget for the FunCube satellite. Okay, so power consumption, we look at a lower consumption FPGA. And this ICE 40, so what I did is I said, okay, what is the tool chain for the ICE 40? Well, guess what? It's not Vivado, which I'm most familiar with. It's Ice Storm. And so this is something that you can clone from GitHub, get up and running with a little bit of help from Google and forums. And then you can go ahead and synthesize, so we simulated last week, simulated the polyphase channelizer, which is looking at the spectrum and figuring out where the signals are, because we're doing successive interference cancellation. We're essentially scanning this bandwidth. Okay, so we synthesized. We got our polyphase channelizer. Simulation looked good. Well, there were some bugs. So plowed through the bugs, and we have this synthesized for the ICE 40, targeted for the specific chip that AMSAT UK wants to use at 87% usage. So pretty good. It originally broke the bank, and what we had to do was to move the magnitude calculations off the FPGA to the general purpose processor. So just like in the Zinc, where we balance between, a general purpose processor and the FPGA fabric, same deal here. We have an STM processor in this design and an ICE 40. And so unlike our other designs where we usually use a very large FPGA and then a relatively small ARM processor, this is the opposite. We have a very capable STM general purpose processor and a smaller FPGA. The synthesis worked at 87% usage, and the max timing is way above what we need. So we need 12 megahertz. It can handle it up to 35, 36 megahertz, depending on how you tweak it. So we're in really good shape for the usage for our channelizer. Now, what happens after that? We pick these channels, we pick the peak signal. We see a signal that's really large, and we send it off to the STM. Now, our understanding was that we would have somebody helping with this part of the project, that on the general purpose processor on this STM microcontroller, that somebody would be handling all of that. Well, we haven't heard from them in a while. So I looked at it and I was like, well, what would it take to do that? And it turns out that the driver for the polyphase wasn't too bad. Most of this is already existing in open source, and it worked and compiled. And holy cow. Okay, so we have a driver. Um, the bitstream is built successfully. The driver compiles. It's ready for a hardware test. And we're using full IQ output. So this is a complex baseband. Originally, it was just real signal only, but I went ahead and said, okay, we need IQ. The setup guide, wiring guides, all of the documentation, everything that somebody like me that's kind of a newbie to STM would need to set it up, all written down. Found a lot of things that needed to be installed from source rather than just installed like say homebrew. So all of that got wrung out over the past week. So now we come to actual hardware and testing and getting it to work over the air. So what do you need? Well, we need this board built, and there is work that's supposed to be happening to build what's called 1U cards. They're about yay big, 1 unit for the 2U spacecraft. And those, our design fits is a 1U and goes ka-chunk, it's part of the spacecraft. And so I know that there's somebody that's supposed to be working on this, but we went ahead and bought 2 dev boards, one for the STM and one for the ICE-40. And we would just have to wire little, connectors. And those wirings are like an SPI bus, a couple of GPIOs, ground, power, stuff like that. Doable, achievable. So I ordered them. I don't know. Okay, that's a sheet of paper to prove that I ordered it, and the background's taking it over. But what I ordered was the Nucleo board. It's 144 pin version, and then the breakout board for the ICE-40, and that's going to be here this week. So what we'll be able to do is to take this design for AMSAT UK and to put it on these boards, get it up and running and working, and prove that the design actually works. So that's the good news. The questions are, how do we deal with the rest of the spacecraft? And so the person that we're supposed to be working with, the lead for this project, has not been available. And so we're now working sort of directly with AMSAT UK, and we now have a set of technical questions for them. And we know that we're getting an IF signal from, so it's from 430 megahertz or so, this 30 kilohertz band. It's at, we know that it's at 10.7 megahertz. That's the IF. We already kind of know some of the signal conditioning. And then we are responsible, it looks like, for the ADC, for the analog to digital conversion. The original design from the lead had a set of analog digital converters, but it does not look like they match very well with just a raw 10.7 megahertz. So they can't sample it directly. It needs 80 kilohertz, delivered to it. So there needs to be some sort of staging to us. But the latest that I have as of yesterday is that this 10.7 megahertz is what we get directly. It's delivered to our part of the project directly. So that means a little more work needs to be done here. So what we're going to focus on, I'm going to set aside the question of the mixer for now, if there is a mixer that needs to be integrated or we need to add it. And I'm going to focus on, let's assume that we have this 30 kilohertz band and then go ahead and like prove that works. And then we'll ask some probably increasingly blunt questions of AMSAT UK about like, okay, so how do we get this down converted? Do we want to have these ADCs that the original designer picked, or do we want to use the ones that are already on the boards? Exactly what sample rate is this before or after AGC? That's a big question, and that actually splits it into 2 different approaches. Is there any particular packet format for any sort of signal? Because what we've talked about so far is like, okay, grappling with the interface. But when we talk about the functionality of the fun cube, we're looking at, this 30 kilohertz, and what do we do with the signals that we find? what we're doing is we're picking out the strongest one, sending it to the processor, picking out the next strongest one, sending it to the processor, and we're picking through until we run out of time and then have to do a whole other sampling of the bandwidth. So let's say we can handle 4 or 5 signals at a time. What do we do with those signals? Are we doing signal identification? Do we assume that they are a particular format? Are we only looking for a small number of formats? Is there an opportunity for machine learning or artificial intelligence or signals identification or autonomous receivers? There's a lot of things that we could deploy. There's a lot of things that we could test. So those are kind of open questions, but all of those things are things that we can do. We're pretty good about the JPL approach for the autonomous receiver. This starts out with identifying what the, like what the characteristics of the signal are. Modulation index is where that starts. And so it essentially extracts features from that particular sample and then heuristically, like from a checklist, determines what the signal is. That's not really machine learning. That's more like an expert system. There are some machine learning models that will take a symbol level or a sample level and within 40 or so symbols determine what what type of signal you have. And it just kind of depends on what they want. So what I'm hoping over the next week is to hear a lot more from AMSAT UK about what exactly they want. And then once you get these signals, where do they get transmitted back down to the Earth through FunCube? Or do we just present the telemetry? Do we just say, look, here's all the signals that we observed? Are we just like an Earth observation signals intelligence reporter for amateur bands? Or what? So anyway, that's the goal. Long term, so the opportunity for showing this, we could, if we have all the hardware and it's working and we can turn it on and scan 70 centimeters, then we can show it off on the 4th of April at B-Sides in San Diego. We can bring it to Friedrichshafen in June. The AMSAT UK people will definitely be there and would like to meet with us, and we can then show it in person. So that would be one of 2 major demos at Friedrichshafen. So for that particular project to support a satellite system, that's kind of where we're going. All right, so I'm going to stop here for questions, comments, and redirections on all of what I've just shared.
Can I ask a question?
Yes, of course.
If you do that, like Meetup with the UK people, will you post that on IEEE?
Oh yeah, I'll be sure to do that. Yes.
Okay, because I think that would be really cool to hear other people talk about it. Is there life out there? So yeah. These signals out there. Okay, thanks.
Yeah, and this we should know more. We should know a lot more over the next week because we'll get the boards in and be able to try it and see what's going on. The technique itself, like the successive interference cancellation technique, is widely used in like cellular 5G, 6, and will be used in 6G, and is it's familiar to certain classes of like commercial DSP folks. In amateur use, though, this might be like the first major use of it to sort of and as far as I know, the first open source kind of example in the community. So it would. What I'm hoping is that it's a really, really good pedagogical like example. Like, oh, so here is successive interference cancellation. Now, do you want to see how it's actually implemented? And for this particular target, for the essentially a spectrum analyzer over 30 kilohertz, it's only 4 channels. So it's a 4-channel polyphase filter bank or channelizer, and the channels overlap so that it's a smooth response across. When we use this design for our communication satellite, what we do is we pull the channels apart and they are channelized, with a gap in between. And that alone is really worth highlighting and showing people that the same polyphase or multi-rate technique can be used in both an analysis, like a spectrum analysis sort of situation, or to channelize it for communications, because we're using it for both. In this fun cube, I would call it narrowband, because 30 kilohertz to me is narrowband, but this narrowband application with the 4 channels, the FFT that we're using is only 64 coefficients. When we use it for our high-for-IA, for the channelizer for, looking down at our uplink, then we have nearly 1,600 coefficients, and we have almost 100 channels. But it's the same design, and it's just parameterized differently. And this sort of reuse, or taking the same open source design, and it can be used in both situations in very different frequency bands, that's good stuff. That's why we're here, to sort of show this sort of design to make it possible. So that's one of the goals. And being able to take it, I think, to Friedrichshafen would be really good. So over the past day, it's pretty clear that the AMSAT UK people will be there, that they really want to see it, that they're very interested in including it. I'm doing all that I can to make sure that our hardware, that we made, is on a satellite from the amateur community. This has been we've made multiple efforts to get involved in multiple satellites for amateur satellite. And, I'm just thrilled if this would work. Oh, yeah. See you, Matthew. Okay, that's it for the report for MDT. I know it's a lot and pretty technical, but when you sort of step back and look at it as a tool to kind of divide up the spectrum, to channelize it, like I'm going to only look at one part at a time, and I'm going to go round and round and round. I'm going to take those samples, and I'm going to go over here, and I'm going to do stuff to them until my time runs out. That's really all that's going on. So the number of channels that you have, 4 in the case of the 30 kilohertz, and 100 in the case of, when we're up at 5 gigahertz. That's just a fairly minor code change, and just make sure that you have enough horsepower in your circuits to do it. Okay, that's all I have on that. All right, any other questions about anything we've already covered?